Hello everyone, I'm Ryan, an astronomer at the Space Telescope Science Institute, where they run massive telescopes like the Hubble Space Telescope. But today I'm going to be talking about a smaller space telescope, one called the Transiting Exoplanet Survey Satellite, which I use for the work that I do, and a whole bunch of other astronomers around the world also use for their work. And as we talk about TESS, we'll be focusing on what its main objective was, which was to discover planets around other stars that are not our sun. These are known as exoplanets. But while searching for exoplanets, we've found a whole lot of other stuff along the way. But before we get into TESS, let's go a little bit back in time and put some groundwork down. So the first space-based satellite to find exoplanets was something called the Kepler Space Telescope. This was launched in 2009 and did incredible work at finding exoplanets all across the sky. So these are planets that orbit stars that are not our sun. And it did an incredible job finding thousands upon thousands of exoplanets. But unfortunately, in 2013, one of its reaction wheels, which keep it pointing steady, broke and it started to wobble. And this meant it couldn't do its primary objective anymore, which was to look at a single patch of sky to study stars very closely to find if there were planets going around them. So instead, the engineers worked out that they could point Kepler around the sky to still kind of continue its mission. But tragically, a few years ago, it ran out of fuel and Kepler was left spinning, abandoned in space. So to this day, Kepler is still adrift, spinning around aimlessly, which is all pretty sad, but it's not the end for exoplanet science in space, because some other satellite was getting prepared, and that was the Transiting Exoplanet Survey Satellite. So this satellite, as you can see here in its near completed stages, was kind of small, but it can do tremendous amounts of science. So just go through a few features of this satellite. One thing that you'll be able to see is that we have two solar panels either side of the satellite itself. Those are used to power the satellite, because without power, it couldn't do anything at all. On the top, we have these four black lids, which cover the cameras which are used to study the sky, and they're protected inside of this big cone. And on the side here, there's this little dish-looking object, which is covered by a tinfoil. Now this is what they actually use to transmit data back to the Earth. So TESS will be in orbit of the Earth for its lifetime collecting data, and when it needs to send information back to astronomers on the ground, it'll use this little dish here to communicate with big radio telescopes on the ground. So TESS is quite a bit smaller than Kepler, and it does a similar kind of science, but the way it does the science is a little bit different. So Kepler was an incredible telescope and only primarily looked in one direction, and this big cone stretching across the night sky. So it was just one patch of the sky which gave it this pencil beam shape. This was fantastic for detecting planets within this cone, but you couldn't see anything outside of it. So we could find planets that are thousands of light years away from us inside of this cone, but we didn't know of anything close to our solar neighborhood, close to the sun. So that's something TESS wants to do. It wants to look at all of the nearby stars to try and find if there are stars close to us that have planets orbiting them. And a cool way of seeing this is on this website here, where it displays all of the exoplanets that Kepler has found. And you can see that there is a massive beam of stars that have exoplanets around them in a particular direction, and that's the direction that Kepler was looking. And then all around in this other direction, in this big wheel, there are lots of other beams where we've discovered planets. And those are the other patches of the sky that Kepler looked at, and they're along something called the ecliptic. But what TESS is doing is looking at the big ball of stuff immediately surrounding us. So it can't see planets out for thousands of light years like Kepler could, but it can find all of the very interesting planets very close to us, which are also very interesting if you want to try and understand the planets in greater detail. So that's the main difference between Kepler and TESS. But before we get into the science that TESS achieved, let's go on to a bit of the instrumentation behind TESS itself. So here's a picture of the final camera assembly of TESS. So TESS has 4 cameras that each look at different parts of the sky, and you can see them here with the little red caps on them. Just note they're a little bit strange shapes, which are to make sure that the cameras all line up correctly and point at the right parts of the sky. But this, once put together, will be the main instrument part of TESS. The rest of it is to do with the cameras and how the system actually operates. But inside of these tubes, there are optical elements like this thing here. So here's one of the project scientists from TESS holding up one of the mock optical elements. So you can see it's something like a fisheye lens. So it collects light from far outside of immediately in front of it. So in this case, you can see this guy standing over here, which isn't directly in line with the lens from our perspective, but you can still see him within the lens. So that's the power of the fisheye lens. It can show you a much larger field of view or area than what you'd be able to see otherwise. And another really cool optical element are these lenses here, which have a kind of filter coating over them. So this coating only lets through particular kinds of light that they're interested in studying. So you can see on the top, it's reflecting all of the blue and green light, and passing through it is all of the red light. So the red light is what they want to fall on the detectors and to study to try and find exoplanets. So in 2018, TESS was loaded up inside of a Falcon 9 fairing, and this is probably the smallest payload that a Falcon 9 has ever launched, but as you'll see later on, it's done some pretty incredible things. So it was launched on April 18th, 2018, and it went up into a very strange but very useful orbit. So here's a little animation of the orbital path of TESS. So this will play a few times so we can get to see what's going on. This green circle around here is the orbit of the moon. The blue dot in the middle is the Earth. And this purple line moving around is the orbit of TESS as time moves on. So as it starts again, we'll see TESS kind of flies away from the Earth. It gets higher and higher, and it gets bumped up by the moon and then starts orbiting around the Earth between the Earth and moon. This orbit of TESS is incredibly particular. In fact, TESS orbits around the Earth every 14 days or so, or twice for every once the moon goes around the Earth. It's what we call an orbital resonance. And this orbital resonance helps keep TESS in an incredibly stable orbit, and it's predicted it should stay in that stable orbit for tens of thousands of years without using any of its onboard fuel. So orbit-wise, TESS can pretty much stay there forever. It'll just be down to how long the optics can live for. So what does the data from TESS look like? It has those 4 cameras which can look at enormous patches of the sky. Here's a little movie showing the strips of TESS's images over the course of the first year. So it's looking at the southern hemisphere, and we can see these enormous strips, which are TESS's 4 cameras covering massive chunks of the sky. Each of these strips covers an area about 4,600 times the size of the full moon in the sky. So if you go out and see the full moon at night, you can try and imagine how big of an area this actually is. There are some cool things inside of this image, like the Magellanic Clouds. There's the large one here and the small one here. And when it gets around to the end part, you can see the Milky Way stretching along the right-hand side. So there's an awful lot of stars in here and an awful lot of science that can be done with this data. Each one of these enormous stamps of the sky is recorded every 30 minutes, and it sits on one of these patches for 27 days before moving on. So there's a whole lot of data that it collects. So the next question is, how do we use this data to actually look for exoplanets? What is it trying to see? On this little diagram here, we can get a sense of what TESS is looking for. So up here we have a yellow star, perhaps something like our sun, and around it we have this black ball, which in this case is an exoplanet, a planet orbiting around this distant star. And on the bottom we have a graph which has the brightness of the star on the y-axis and just time along the x-axis. So it could be in days, it could be in minutes, but time just progresses along the x-axis. So what we see is that if a planet moves in front of its star from our perspective, the brightness of the star will drop ever so slightly while the planet is in front of it, and then go back up again once the planet leaves the surface of the star. This change is incredibly small, perhaps only a few percent the total energy of that star, but it is something that the very sensitive cameras of TESS can actually detect. And this little dip can tell us lots of interesting things, like it can tell us how big the planet is relative to the star, and if we measure lots of these dips, we can tell how far away that planet is from the star. And the bigger the planet is, the deeper the dip, the smaller the planet is, the smaller the dip. So you can think these things through. So this is kind of the most easiest visualization of the data. Let's go to some real data that TESS actually took. So this is a plot from a paper, a scientific paper. So it's a little bit complicated, but we'll be able to go through it and understand what it says. So again, on the y-axis, it tells us the brightness of the star. And along the x-axis, again, we have some kind of time. It's not exactly days anymore, but it is pretty much days. So you can see as time goes on, this brightness of the star is pretty steady, and then suddenly it drops down and then goes back up, and goes along again, drops down a little bit, and then comes back up. So these two areas are the areas that we want to look at. So this one in particular tells us that, oh, there must be a planet orbiting around this star. And it's a pretty big planet if it makes a change of about 1% in the star's brightness, the star being WASP 18b. So that's the planet crossing in front of the star, but there's also another little dip here, which is the planet itself going behind the star. So not only does the planet kind of cast a shadow on us as it goes in front of the star, but it also reflects some of the starlight back at us when it's to the side of the star. So when it goes behind the star, it's not reflecting light anymore that we can see. So the star's brightness dips ever so slightly. This second panel is just kind of a zoom in to the top one. And then this bottom one is the result of where they fit a model to the data that TESS collected. This red line is the model. And they subtract that model away from the data and see what remains. And this remaining stuff is just the error in the measurements. So in this case, it's saying that the measurements TESS took were incredibly precise. So this is how TESS finds planets. It looks at them incredibly carefully to try and spot these little dips in brightness. And then we can fit models and do lots of science on this data to understand what it's actually doing. So that's the process, but what planets has TESS actually discovered? We'll cover a few interesting ones. So this one here is TOI 1338b. TOI just stands for target of interest, and that number afterwards just means the number of interest it was, and B stands for the planet. And this planet's really cool because it may be familiar for people that have seen Star Wars. There's a planet in Star Wars called Tatooine where there's two stars orbiting around each other in the center, one about the same size as our sun, one much smaller than the sun, and there's this planet orbiting around it. This planet's something like a gas giant, so it's nothing like the Earth or Tatooine in the Star Wars movies. So this planet is about 1,300 light years away from us, so there isn't really much hope of being able to go there and see it. So it can spot it can spot planets that are perhaps out of movies, so that's really cool. And there is another really cool thing it's found is this star system here. oh sorry, this planetary system. So again, we have a small star, and if you look for long enough, you see one planet cross in front. It has a very nice dip in the brightness of the star. Wait some more, and another planet crosses, has a little bit of a different dip through the brightness. And if we wait some more time, finally we'll see a third planet come along and create another nice dip in that star's brightness. You'll notice that those three dips are a little bit different, and they tell us different things about the orbits of these planets. The first one is reasonably deep and nice and regular. The second one's kind of sharp and not like the others, and that sharpness tells us that it orbits the star a little bit off center from our perspective. But that's the planetary system there, and the really cool thing is this final one, TOI 700d, is just within what we call the habitable zone of that star. So it's the area around that star where the temperature on the surface of TOI 700d should be high enough that there is liquid water on the surface of the planet, and low enough that that liquid water doesn't boil away. So TOI 700d is only 100 light years away, and it's a target of considerable interest for scientists across the world wanting to use bigger, more sensitive telescopes to try and understand what this planet might be, if it has an atmosphere, if it could be somewhere that has life on it, all of these kind of very interesting questions. But aside from planets, TESS has also found something else which I think is really cool, something called an exocomet. So again, these are some plots from a scientific paper, so a little bit complicated. But on the top here, we have the light curve from a star called Beta Pictoris, which is about 63 light years away. You can see the brightness wiggles around an awful lot over time. But with models we have to predict how stars behave, you can fit those models to that wiggling brightness and take away those models, and you're left with a nice, easy, flat line with brightness. And if you look very carefully on that flat line, you'll see these little dips here. They're a bit different to what we've seen before. So it's the same kind of principle as what we saw with exoplanets, but you'll notice that these dips aren't very symmetrical. They are sharper on one side and more drawn out on another side. In particular, you can see it very well in this one on the right-hand side. It looks like a shark tooth. Now, this isn't a result of an exoplanet going in front of the star, and this star is pretty young. It's only about 23 million years old. So this led astronomers to the conclusion that it's not planets that we're looking at, but gigantic comets that are going around the star. So you can see here an artist's impression of this stellar environment. So we have the star sitting at the center, then these enormous comets. And again, like we can do with the exoplanets to work out their relative size, we can use these same techniques to work out the relative sizes of these exocomets and their tails. And we can find that there's about between the size of the Earth and the size of Jupiter. So these tails of these comets are extremely enormous. But to date, TESS has only found about 50 confirmed exoplanets, but there are a few thousand more planets yet to be confirmed. And one place in Australia which is really helping to try and understand how many more planets there are that TESS has found is this telescope facility here called Minerva Australis, which uses a series of telescopes to investigate targets of interest from TESS and try and confirm if they are planets or not. So that's a really cool project in Australia, which is directly benefiting the science and the hunt for planets from TESS relating to NASA. But aside from planets, TESS has also done really interesting stuff with stars. So there are some stars which kind of pulse. So here's a few basic models of stars kind of pulsing and changing around. So their surface kind of rings like a drum. And we can model how these stars will pulse and move and the effects that will have on how bright that star is over time, like we saw with Beta Pictoris. But there's one pulsating star which TESS has found which is like no other we've seen before. This one here is called HD 74423, and it's about 1.7 times more massive than our Sun, but it's got a cool companion sitting next to it. And this companion is so close that the gravitational pull of the companion changes the surface of the star. So it's not a sphere, but instead it's kind of a teardrop shape. And this has some other very interesting effects where the pulsations of the star, so getting bigger and brighter and dimmer, bigger and smaller, occur only on the side which is facing the companion star. So this is something that was predicted for quite some time, but this was the first time that it was actually seen. So that's a really cool achievement from TESS, and hopefully it will find some more as it scours the entire sky. But aside from stars and their strange pulsations, TESS has also found something which is more interesting to me, which is the death of stars. In one case, it found an enormous black hole tearing to pieces a star, and something called a tidal disruption event. So if a star gets too close to a massive spinning black hole, it will tear that star into pieces and create a big string of material. The star gets spaghettified, and the very hot core of that star gets exposed to space and glows very brightly as it goes around and bumps around, trying to escape or fall into this black hole. And if we go and look and see what TESS actually sees of this crazy event, it's something like this. So again, it's a scientific plot. We've got different axes, but they're still meaning the same kind of thing. So along the y-axis, we have, again, the brightness, and along the x-axis, we have, again, time in days. So TESS saw these red points along the bottom here. So over the space of about 40 days, this star getting torn to pieces got very, very bright, and then it slowly starts dropping away again. And this is very interesting because it's the first time we've actually seen the brightening of this event, and they triggered a whole bunch of different telescopes to observe this, like we can see in these other bits of data sitting above the TESS light curve, which are just observations taken in different colors, which can tell us different bits of information about this event. So they found a whole bunch of cool things with this, one of them being that the temperature of this tidal disruption event dropped incredibly quickly. So as the star was torn to pieces, all of the temperature kind of radiated into space very, very quickly. But this is a black hole tearing stars apart. What TESS has also found are stars just blowing themselves up. So things like this here, which is known as a supernova, happen all across the sky. So if you look at large areas of the sky, you're bound to spot one or two, and they're incredibly bright. So you can see them for enormous distances across space. So in this case, this supernova was a core collapse supernova. So a big star just collapsed on itself and blew up and created, in this case, the Crab Nebula, which is a nebula familiar to our skies. So if we look at this little video here, it shows a time series of some of the supernova that TESS found. So again, these plots tell us brightness against time. So you can see all these supernova have similar shapes. They get bright over a number of days and then slowly start fading away. And these supernova are very interesting to study because we can get precise information about how these stars actually blew up, which is incredibly important to scientists like myself who want to try and understand why stars blow up, how they blow up, and what we can use that information for in terms of understanding how our universe changes and evolves over time. So on this topic of exploding stars and stuff that I do, let's finish on a little bit of science which has been going on over the last week or so. So TESS has been doing what it's doing and looking at patches of the sky. And in one of those patches of the sky, there was this lovely merging galaxy here, where we have two galaxies merging together, which is cool in its own right. But the really cool thing is that there was a supernova that went off inside of this galaxy. And a telescope on the ground spotted that supernova only about a day or two after it actually blew up, which is incredibly quickly. And we realized that the supernova was actually observed by TESS, which means that we would be able to see the very, very early stages of the star actually blowing up, which, as I mentioned before, is very important. So what my research group did is triggered a whole bunch of telescopes to take observations of this. So one of the telescopes was the Hubble Space Telescope, which went and looked at this star as it exploded, and the Swift Space Telescope, which also visited this object and took lots of observations to see how bright it gets in ultraviolet light as it explodes. So both Hubble and Swift looked for ultraviolet light. And over time, we also had a whole bunch of ground-based telescopes, which also looked at the same thing. So we're going to have an enormous amount of data on this one star blowing up, which should be able to give us really good information on the star itself before it blew up, and help us understand how these massive stars actually blow up in the first place. So this is a bit of ongoing science which I'm involved with, which is really exciting and just goes to show how useful and versatile TESS has been, even though it was intended to just look for exoplanets. So just to recap, what have we found while hunting for planets? Well, we've of course found exoplanets, 50 so far, but thousands yet to be uncovered. Found something that no one really expected, which were exocomets orbiting Beta Pictoris. We've found strange pulsating teardrop stars. We've found hungry black holes that have been eating stars, and we've found stars that have been blowing up. So we've learned a lot in the last 2 years from TESS, and as TESS goes into the future and takes more observations of the sky, we're bound to learn even more, and it's an incredibly exciting experiment to be part of. So with that said, we have some time for questions, so let's get into those.